Welcome to the power system protection lecture. It is lecture number 2. Also same will continue the introduction part. Last class we discussed very briefly the introduction to the power system and also various types of faults, sound faults, series faults. Very briefly we described. Now in this class we will talk about little detail about the power system faults. What happens when the disturbance is there, the faults are there. So let us see the phasor diagram of voltages and currents during various faults. In fact, if we will consider the sound faults, there are 11 types of sound faults, that is considering various phase to ground, various phase to phase faults. So let us see the phasor diagram of various voltages and currents during these 11 types of sound faults. So let us first consider here the triple L fault, that is 3-phase fault, right? So 3-phase fault means your the voltage will be very drastically dropped in all the 3 phases simultaneously, and it will remain balanced all over during the fault as well. So this is 3-phase fault without involving the ground. Similarly, if we involve the ground, that is 3-phase to ground fault. So we can say here, you can see here similar type of drop in the voltage, very drastic drop in the voltage, whereas the current will increase very drastically. It will increase. So we can see here that this is the 3-phase fault, or we can say the symmetrical fault. Now we will consider the line to line fault without involving the ground, that is line to line fault. This is line to line fault that is phase to phase fault between A and B, that is the fault when the phase A and phase B are short circuited without involving the ground. Similarly, the voltage also decreases, we can see here, and the phase and the fault voltage, that is here, fault voltage will lag obviously. Like if you will see the circuit here, let us say this is your network and this is phase A, phase B, and sorry, just a minute, phase A, phase B, and phase C here. So phase A and B are shorted, right? So let us say the current is flowing from A to B. Okay, let us say it is from A to B. Then obviously the voltage during the fault will lag the original voltage VA. Okay, this is original VA, right, with before fault. So VA during fault will lag before fault voltage. Similarly, your phase B voltage will also lead the during fault voltage at phase B will lead the original voltage, that is before fault. Okay, so this similarly we can analyze the fault between A and C and fault between B and C, right? We can see here right away. Similarly, we can see the fault between line to ground fault. Okay, so that is single phase to ground fault, where we can see here only the voltage is dropping in phase A when the fault is between A and ground, phase A and ground, and similarly the voltage at phase B is dropping when the fault is between phase B and ground. And similarly for C and G we can see the voltage is dropping, right, at phase C. Okay, so now we can see here again line to ground fault, that is double line to ground fault, or we can say phase to ground fault, right. Here in this case, when the fault is between A, B and ground, the magnitude will decrease very drastically in phase A and phase B, and obviously phase A voltage will lag the original voltage before fault, and phase B voltage will lead the before fault voltage at phase B. Similarly, it will happen also when the fault is between A, C and G and B, C and G. So these are the sample phasor diagrams when for various types of sound faults, that is 11 types of sound faults. So now we'll talk about the series fault. In case of series fault, in fact series fault happens when the conductor is, suppose there is a transmission line, and series fault happens when there is a breakdown in the conductor because of some natural calamity or natural disaster. So the consequence is not very serious unless the open conductor, that means the conductor is open here, unless the conductor touches the ground. So unless it is touching the ground, the consequence is not very serious. And also sometimes this type of series faults happen in the field winding of DC and AC machines. Sometimes when the field winding is open circuited, it has a very serious consequences. Similarly, we know this in the subject machine subject, we have studied this. When the field circuit will be open circuited, there is a chance that when that flux becomes zero, and therefore the speed of the machine drastically increases, very high speed it attains, and because of that it damages the rotor. So in the open circuit, sometimes the open circuit in the secondary winding of CT also happens. When the secondary winding of the CT becomes open circuited, there is a chance of producing high voltage in the circuit. So let us consider the abnormal operating condition. Till now we talked about the faults, series faults and sound faults. Now we will talk about the abnormal operating condition. So let us see, should protective relays trip during the abnormal operating condition? If the abnormal operating condition is leading towards some kind of instability, then obviously it should trip. But unless that, it should not trip, because there are certainly certain abnormal conditions happens, like your we can say your inverse magnetizing current in transformer. It is very high. It is sometimes it becomes more than the fault current, right? And because of this inverse current is because it is very huge value. So therefore, sometimes if your relay is not set properly, then sometimes it trips. So it actually it is not intended to be tripped, but it becomes tripped during the abnormal conditions. So another question is, can protective relays prevent faults? So obviously protective relays, it cannot prevent fault, but we can protect the system from the fault condition. As soon as the fault is isolated, it is better for the system and the system can revive very quickly. So therefore protective relay cannot prevent fault, but it can protect the system, protect the elements of the power system, right? So what are the protective relays supposed to do? In fact, protective relays is required. These are required for protecting the system. As soon as the fault happens, it should isolate the faulty part of the system so that it should not propagate. The fault should not propagate to the system, throughout the system. So let us see the evolution of power system. How the power system evolved. In fact, when the power system started in initial days, it was called the isolated power system. Isolated means only one generator sometimes supplying power to a community, to a campus, something like that. So that is called isolated power system. That means few generators they are supplying at a load center. That is isolated power system. And in fact, isolated power system is easy. In fact, if some fault happens, it is very easily handled, or there is no chance of propagating the fault in case of isolated power system. But it has certain drawbacks or disadvantages. So the drawbacks are like we cannot have a reliable power supply system. We cannot have a reliable power supply. Okay, it is difficult to get a reliable power supply from isolated power system. Cannot have. So therefore gradually the interconnected power system came into picture. So in case of interconnected power system, the reliability is maintained well. So reliability is maintained very well, because if somewhere the fault, reliability is maintained. Somewhere the fault happens, then at that particular zone or particular area the fault can be isolated, and other part of the power system can supply power to the as soon as to the area where the fault happened, right? It is very easy. Only the small section, small part of the system is isolated and other part is maintained well. So by that way the reliability is maintained. And another benefit of the interconnected power system is economic operation of the power system, where the power system can be operated economically by using the economic load dispatch method. And also as we know, there are certain disadvantages also in the interconnected power system. The major disadvantage is maintaining the stability of the system, because as soon as there will be certain disturbance in the system, then obviously sometime if it is not stabilized, then the disturbance is propagated to the other part of the system. So this is the disadvantage of interconnected power system. Now we can see here a very typical interconnected power system. Right, here we can see the interconnected power system, which is having 3 generators and loads also, and the transmission lines are maintained at 400 kV, you can see. And obviously the transmission lines are equipped with the circuit breakers, and the generators are generating in fact at 20 kV, and the power will be transmitted at 400 kV after stepping up the voltage using the step up transformer, transmission or you can say power transformer, which is having a step of ratio of 220. So when suppose the fault is happening here somewhere, let us say in this line the fault happened, the circuit breaker at both the end will isolate this transmission line, but in fact the loads will be supplied through the generators, various generators, because this is interconnected, so the reliability of the supply is maintained in this system. Similarly, the economic operation can be handled very easily. I hope you have studied the economic load dispatch during your last course. Okay, so let us see. The next one is your negative synergy of an interconnected power system. I already explained what are the negative synergy of the interconnected power system. Already I told that the stability is the main problem, the issues in the stability of the system, because in fact the power system, steady operation of the power system is difficult, very difficult in case of interconnected power system, because there are loads, various, sometimes the loads are increasing, decreasing, the disturbance is continuous in an interconnected power system, and also along with that the faults are also happening. So there, in fact, this leads to the various issues related to the stability of the system, and sometimes this causes a catastrophic stability issues, and the system may become unstable, and sometimes it becomes blackout also if the proper arrangement is not made, or proper protection schemes are not being in use. Then let us see the various states of the operation of our system. What are the various states? So already we know, under normal state the power system operates under when the load is equal to the generation. In fact, practically it doesn't happen. In fact, it never happens that the total load in the system becomes equal to the total generation of the system, because as I told, the disturbance is continuous in the system, so it is difficult to achieve exactly the steady state condition in the power system. But for analysis purpose we assume a steady state condition. Another issue is from natural monopoly to deregulated power system. Now power system is completely deregulated, and in the generator section, in generation sector, there are many private participants. It is dismantled, and we can say unbundled, right? And in the distribution section also, it is sector also it happened, and because of this the competition has been introduced in the system, and because of that sometimes the market power issues come into picture, sometimes the right of way, there are a lot of issues, transmission of electricity, there are a lot of issues comes into picture because of the deregulation of the power system. So let us see then various states of power system. There are 5 states in the literature. You will find there are 5 states in the power system. We call it in fact 5-state model. Okay, so 5-state model. We are seeing here 5 states. One is normal state, alert state, emergency state, in extremis state, and restorative state. Right? These are the 5 states. Under normal state we know that total load, there is no violation of any constant. That means total load in the system, that is, we can say PD is equal to total PG, sum of PG equal to sum of PD. So there is no violation of the system constants like line parameter violation or operating constant. So L indicates the line constants, and O indicates the operational constant. So there is no violation of line and operational constants. Okay. So now, if as I told that it is very difficult to achieve normal state or steady state in a power system, very difficult. It is not possible at all. So continually some disturbances happen in the system. As soon as there is some disturbance happens and or some contingency take place, then the power system achieves the alert state. Under this alert state, your constant violation takes place. So your constants are two types I told, line and operational constant. So in fact here in alert state, it is in the verge of violating the constant. In fact it doesn't violate the constant, but it is in the verge of violating the constant. So that means it is under the power system is operating at the boundary condition. Okay. and at this condition, when the system is operating under alert condition, at this point, if the system operator takes some action, then obviously the power system returns back to the normal state. Okay. So if the system operator unable to take any action, and certainly some disturbance took place, then the system goes to emergency state, where the line and operating constant, among the line and operating constant, the line constant is violated. Okay. So the line constant is violated. I will mark it as L bar. Okay. Now from emergency state, if obviously from emergency state it transit to the in extremis state, then the operational constant also violated here. L and O both are violated here. Okay. So therefore in extremis condition or in extremis state, both the line constant and the operational constant are violated. What is line constant? I just forgot to tell you. Line constant is marked as L, and it is in fact violating the maximum line flow violation rate. And that includes the thermal limit, other limits. And in fact the operational constraints that is represented as O, it is consisting of V, the voltage and frequency of the system. Because voltage has certain range, within that range the voltage should be maintained and it should not be violated, the voltage, and also frequency of the system has certain range. That is, in case of India we have the frequency range is 49.5 to 50.2, something like that. This is the range in India. So there should not be any violation of voltage and frequency. That is the operational constant. Okay. So now from in extremis state also sometime achieved directly from alert state if both the line and operational constants are violated. Okay. Now from the in extremis state, it goes to the restorative state. So where the operator takes action to restore the system. So then from the restorative state it can go to the alert state or it can go to the normal state. So this is in fact the 5-state model, and this plays very important role in fact in designing the protection system in the power system. Based on these various constraints and considering the characteristics of the various states, the protection schemes can be designed. So we call it system integrity protection scheme. We call it SIPS sometime. So that is system integrity protection scheme. Okay, so this is the 5-state model. Now let us see the various types of protection that is available in power system. One is your apparatus protection. Okay, apparatus protection means the schemes are designed to protect the apparatus in the power system, and in that it includes the transmission and distribution line protection. This is very important. And then your transformer protection, then your generator protection, then your bus bar protection. Right? And also along with that, if some large motors are there in the industrial sector, that is also important to protect. And second one is your system protection. In system protection we have out of step protection, where if some generators are going out of step from the synchronism condition, and that protection scheme will just isolate that generator without hampering the system stability. And then your under frequency protection, when the frequency goes beyond certain frequency range, then the system needs the protection scheme needs to isolate the disturbances that is causing the frequency drop or frequency increase. Sometimes the frequency is dropped because of the very huge load demand or load drawal by the different entities or different beyond the entitlements. Therefore, and then the under frequency happens, and considering that, the protection scheme in fact takes action by curtailing that load at that particular zone, so that it will protect the frequency of the system. Rate of change of frequency protection, that is when the rate of change of frequency is very high, that is very increased with increased value, then obviously sometime the protection schemes take action. In fact, nowadays we have the high speed phasor measurement units which captures these signals, this rate of change of frequency protection, and because of that the protection scheme acts. Then fourth one is your islanding system protection. Islanding protection system protection is your protection scheme where because of some region in some fault happens in the transmission line, and the system has adequate generating capacity, then that particular zone can be islanded and it can be operated in islanded mode. So that kind of protection facilities also can be designed. So basically broadly we can classify the protection schemes into two types. One is apparatus protection, second one is system protection. And in the apparatus protection we have these schemes: transmission and distribution line protection, transformer protection, generation protection, bus bar protection. So we will cover all these protection of apparatus protection schemes, okay, various protection schemes, and also we will cover few of the system protection schemes, not much beyond this. So more will focus on the apparatus protection. Let us see a brief introduction, very little. I will just introduce a general scheme of protection system, how it acts or how how it is, what are the components and how it behaves. Okay, now we can see in the first figure here, this is a protection scheme for a transmission line where we have CTs and VT. CT and VT, they are the sensors, they are the transducers. They in fact measure the current and voltage, and the signal is being fed to the relay, and in fact the relay is the brain behind taking action. So therefore the relay takes action. In fact, it gives signal to the circuit breaker whether it needs to be tripped or not, right? So this is what the scheme says. In fact, in relay we need sometime only current signal or sometime current and voltage, both the signal, right? If it's directional, if the relay is having a directional element, then obviously we need both the signal, current and voltage signal. Okay. And if it is not a directional relay, then obviously only current signal is sufficient. So now we'll see the simple relays. What is relay? So relay is something like, it's like something like a computing facility is there if it is a numerical relay, or else if it is electromechanical relay, the electromagnetic, because of the electromagnetic principles, the magnet acts on the disk, and therefore it gives a trip signal to the circuit breaker. So in fact, to relay we feed the current from CT and voltage from the PT, that is the potential transformer, and based on those signals it decides the trip signal, whether it has to be 0 or 1, then it sends to the circuit breaker. Okay. Means your circuit breaker should trip. And obviously we have certain setting panels in order to set the relay. Okay. So what are the major components in a city, sorry, in a protection scheme, protection system? The major components are CT, that is current transformer, PT, potential transformer, then relay, which is the brain of the protection scheme, and the circuit breaker, which is the functional or operational element in the protection scheme. So these are the major components: CT, PT, relay, and circuit breaker. Okay. So we'll see now the relay, evolution of relay, how the relays are being evolved, and finally now we are having the numerical relays. So if we zoom into a relay, we can see 3 different types of realization. Electromechanical relay, second one is your solid state relay, third one is your numerical relay. So we'll talk about these 3 relays one by one: electromechanical relay, solid state relay, and numerical relay. Okay. So let us see the electromechanical relay. So it's the first generation of relay, uses the principle of electromechanical energy conversion. Like it uses the principle of electromechanical energy conversion. It is immune to electromagnetic interference and rugged. So like you can see here, the very classical electromechanical relay here. This is we are having the time delay, time dial, and where we can set the time delay. Then we have the aluminum disc here, right? This is the aluminum disc, and this is the time dial setting, and there are certain auxiliary coils. So this is very classical old relay. Now you can see we have because of this is a current, right, where this current is being fed to the electromagnet. Okay, so we'll go into the detail, and it produces the magnetic field. So introduction, the interaction of the magnetic field and the current, this in fact produces a torque which is directly proportional to Im square by 2, and in fact we'll do it in detail when we'll study the detailed constructional feature and the analysis of the electromechanical relay. Okay, so let us go ahead with the solid state relay. These relays were developed with the advent of the transistors, operational amplifiers, etc. After development of the op-amps and the transistors, these relays came into picture. Their functionality is through various operations like comparators. So basically these relays were designed by the comparators, using the comparators, and their main advantages are these are more flexible, and the self-checking facility is there, where it can check whether if there is some fault is there inside the relay itself, and less power consumption and low burden, then improved dynamic performance characteristic. Okay, it has a improved dynamic performance characteristic. Then high seismic withstand capacity. If there is some earthquake or something happens, in fact it operates. Okay. Then the reduced panel space. The panel space required by this kind of relay is very less. We can see here the basic relay structure, very small, and it can handle a lot of aspects. Okay. The next is numerical relays. The operation of a numerical relay involves analog to digital conversion of voltage and current. So in fact, in numerical relay, it computes the after computation it gives the signals by using the current and voltage signal. So therefore the current and voltage signal, the analog signal, has to be converted to the digital form, which is obtained from VTs and CTs. These samples are fed to the microprocessor or DSP, where the protection algorithms process these signals and necessary decisions are taken. Okay. So this is basically a microprocessor. It is imbibed with a microprocessor or a DSP kit, where the digital signals are fed after digitalizing, after the samples are taken from the current and voltage transformers. So you can see a block diagram of the digital relay, where the CT is feeding to a to D converter, analog to digital converter, and VT is also feeding to A to D converter. The digital signals are being fed to the microprocessor or DSP, where it's a microprocessor or DSP kit, which after computation it gives the signal to the circuit breaker, whether it is to be tripped or not. Okay. So it has very special advantages. The first advantage is maximum flexibility. So flexibility is more. It can be changed to any type of relay, right? Because it's a DSP kit, so based on the programming we can change the configuration of the relay, and it provides multiple functionality in the sense that not only it gives signal to the circuit breaker, it can also be used for measurement purpose, right? And self-checking and communication facility. It has also various communication ports or various communication protocols through which it can communicate to the control center, to the to the substation. It can be made adaptive also. Adaptive in the sense that if you want to change the settings, it can be done automatically, right? The settings can be changed. Then the last component is a circuit breaker. A circuit breaker is basically a switch to interrupt the flow of current, because during fault the high current flows, so it requires that we should isolate the system, isolate that faulty part. So in order to isolate that, we need to switch interrupt the flow of the high current. It opens on relay command. Obviously it has to handle large voltages and currents. The inductive nature of power system results in arcing between the terminals of SCB. Okay, so the inductive nature of the power system, it results in the arcing between the terminals of SCB. CBs are categorized based on the interrupting medium used. So their names are being given to the circuit breakers based on the quenching medium or the interrupting medium that is available in the circuit breaker, like oil circuit breaker, or the, you can say, the air circuit breaker, vacuum circuit breaker, SF6 circuit breaker. These are the mediums for quenching the arc, because the arc is being produced in the circuit breaker, right? We'll talk about more circuit breaker in the later classes. Okay, so we'll stop here. Next class we'll discuss the attributes of the protection system, CTs and PTs. Okay, thank you very much.